Welcome to episode 3 in the series about representing data. This one's all about images. We're going to talk about what a pixel is and how they're used in images. Talk about bitmaps, work out the sizes of those using the resolution and color depth. We'll do some calculations to work out bitmap image file sizes. And then we'll use some simple binary data to make a simple black and white image. Right, how do we represent images using binary? Clue there, bottom right hand corner, lots of little blocks. But that's not how we see images. We see it as analog, continuous light waves hitting our eyes, which go at different frequencies to represent different colors. The computer doesn't see that. It sees those continuous waves and has to turn them into signals, into digital signals, and turn those into binary. It breaks those images down into pixels, the tiny little squares, and each one of those pixels, it gives a binary representation. So what is a pixel? It's a small dot in an image, a small square in an image, and you put them all together, you get a bigger image. The more pixels, the better the image. Simply, if the image is black and white, then every single pixel, every single square, is either a 1 or a 0. And then you decide what that 1, if it's a black or if it's a white. So in the example there, we're making 1s black. So that top row is a whole load of whites, so that'd be a whole load of zeros. And that's how you get that top line here, 0, 0, 0, 0, 0, 0, 0. Then, if you look at this one, we've got white, white, black. So it's white, remember, is 0, so it's 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. Look down here. 0, 0, 1, 0, 0, 1. 4 zeros, 4 zeros, 1, and then 2 zeros. And so on. 3 zeros and a 1, 2 zeros, 3 zeros, a 1, 2 zeros, and eventually you'll make this image. And in fact, if you actually look at the patterns of 1s there, it represents the image you can see. How do we work out file sizes? Need to know two things. How many pixels do we have? And then for each of those pixels, we're going to record the color in there. And to do that, that's known as a color depth. How do you find the number of pixels? Well, really, the number of rows multiplied by the number of columns will give you the total number of pixels. Simply put, if you had 4 rows and 4 columns, each of those is a pixel, you'll have 16 pixels. The color depth is the number of bits you assign to represent a color. 1 bit can only have 2 values, a 1 or a 0, so you can only have 2 colors. 2 bits can have 4 values, 0, 0, 0, 1, 1, 0, and 1, 1, so you could have white, light grey, dark grey, black. 3 bits, well now you can have 8 different colors, and so on. Let's look at an example. Here we have a 10 by 10 image, color depth of 1 bit, because it's only black and white, so black or white, 1 bit can hold 2 colors. So the size of that image is 100 bits, because you have 10 rows by 10 columns, that's 100 pixels, multiplied by the color depth, which is 1, that will get you 100 bits. Now remember, it's bits, so sometimes they'll ask you for bytes, so you have to divide that by 8 to get bytes. So file size is number of pixels multiplied by the color depth, or the space needed to store 1 pixel. A little bit more about color depth. If you want 2 colors, black and white, it's 1 bit. If you need 4 colors, it's 2 bits. 8 is 3 bits. So sort of think about that. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. So you can sort of see how you can try and work it out. So if you had 2 to the power of 4, that's 16. So that means you can have 16 different colors. So old computer screens, they had 256 different colors. That was 8 bits. Have you ever heard of 8-bit computing? 8-bit games. That's where that comes from. And photo quality, good enough for our human eyes to be fooled, is where we use 24 bits. 2 to the power of 24, which is nearly 17 million different colors. Now, pop there at the bottom, they do try and trick you because you're so used to using this previous formula here, number of pixels multiplied by the space needed to store 1 pixel, or the color depth. You'll get used to just thinking, oh, it's 3 colors, that must be multiplied by 3. No, 3 colors would require you to use 2 bits. So actually it'd be a multiplying by 2. So they always try and catch it out there. So watch out. Are they talking about the color depth, or are they talking about the number of colors? If it's the number of colors, you've got to work out, well, how many bits would I need to store that many colors? How can the number of pixels and the color depth affect the size of an image? Well, you might have heard of RGB. This is a mix of red, greens and blues, which is how we make up colors on computer systems. What you do is you assign a binary value to each of those values, the amount of red, the amount of green, the amount of blue. So for example, if it's all ones, it'd be full, for red, it'd be full on red. If you had 0 greens and 0 blues, well, it'd just be the color red. Because using a load of binary numbers can get confusing or take longer to read or to write out, normally they convert this into hexadecimal so that you, for example, happen to use a byte, which is 8 bits, you only need to use 2 hexadecimal images. So you might see this kind of thing for colors on the web or in applications, like looking like this. So using a hexadecimal code, FF, so that's full red, so that's loads of ones if you think about it. And then no green is the next 2 digits, and the next 2 digits are not blue, so you know this would be the color red. If you wanted to convert that to a binary number, well, what is F? That's 15. What's 15 in binary using 4 digits? 1 1 1 1. So it's FF, so that's 4 ones and 4 ones, and the rest are zeros. So you're going to have a number that looks like that if you converted it. And remember, if you use 8 bits, you're using 1 byte to represent each of those colors. So looking at this one here, 3 bytes are used to represent that color, or 24 bits. So think about that. All of that data just gets you 1 pixel, and you need thousands of pixels in an image, and they need at least 3 bytes of data. So that's a lot of data to create an image. You think about a high resolution image, 1 frame from a video, say 1080p, that's 1920 multiplied by 1080, that gets you the number of pixels and then the color depth for each of those. So that's an awful lot. If you use an awful lot of data to store colors, then the size of the image is going to go up. If you think about the file size was the number of pixels multiplied by the color depth, well, if you have a very high color depth, the size of the image is going to go up. If you have a very high number of pixels, the size of the image is going to go up. If you up those, then the quality goes up. The quality goes up, I'm afraid the size of the image will go up. And vice versa. If you reduce the size of your image, normally you've got to make a trade-off in number of pixels or color depth. Think about this. If an image had 2-bit color depth, that's 4 different values it could be, 4 different colors it could be. That's now a bigger file than a black and white image because you've got more colors, got a better color depth. But now that means more data needs to be stored, so therefore the size of the file is going to get bigger. The more colors, the better quality. The more colors, the bigger file size. The more pixels, the better quality. The more pixels, the larger file size. So, in summary, the more space you save, the lower quality, and vice versa. Little example there. Each time, the size of this file is getting reduced and reduced and reduced and reduced, but then if you look at the quality each time, the quality is being reduced and reduced and reduced until it's really unrecognizable. There's always a trade-off for file size and quality. Summary again, the more pixels, the better quality, the bigger the file. The more colors you're storing, the better quality, but the bigger the file. You try. Have a look at those, pause this video, write them down, and we'll go through the answers when you restart the video. Welcome back. So what is the color depth of a black and white image? Well, 1 bit. There are only 2 colours. There's only white and there's only black. So it's 2 bits. Sorry, 1 bit, 2 colours. See how you can get confused there? 2 colours, 1 bit. If a black and white image is 4 columns across by 8 rows down, how many bytes would it take to store? Oh, trying to catch you out there, talking about bytes. Because remember, the calculation you make is going to be in bits. So 4 by 8 is going to give you 32 pixels. Black and white, so the colour depth is going to be 1. So it's going to be 32 times 1, or 4 times 8 times 1. But that's going to be in bits. How do we go from bits to bytes? We divide by 8. So that means you'll have to divide 32 by 8, which will get you 4 bytes. Question 3. If an image has 16 different colours, so you see what they're doing there, 16 different colours. I'm not talking about the colour depth is 16. So if your calculations have been multiplying by 16, you're going to be wrong. It says it has 16 different colours. So right now you've got to think, well, okay, how many bits as a minimum would I need to store 16 colours? Alright, well, think about 1 bit is 2 colours. 2 bits, double that, is 4 colours. 3 bits, double it again, is 8 colours. That's not going to be enough. 4 bits is going to be, double that again, 16. So it's going to be 4 bits. So the colour depth is going to be 4. There's 8 columns by 8 rows. The number of pixels is going to be 8 times 8. So it's going to be 8 times 8 to get the number of pixels, multiplied by the colour depth, which you now know is 4. But look, it wants it in bytes, not bits. So the answer that's going to give you is bits. So divide by 8, and that's going to get you the answer in bytes. Now, one thing to do, you don't have a calculator in the exam, so a lot of the times you're trying to look for, as soon as you can, if you know the answer's got to be in bytes, divide by 8 at any point to try and get rid of that calculation at the end. So if we look at this bit here, image is 8 by 8, we're going to divide by 8 at any point, so just get rid of one of these 8s, because if just divide that by 8, gets rid of this. So that now means that you've got 1 times 8 times 4, which is a much easier calculation, because it's 8 times 4, which is 32. You could work it all out. You could go 8 times 8, 64, then divide that, then multiply that by 4 to get you that number, and then divide that by 8 to get you 32. But me, personally, if I'm going to divide by 8, at some point, when we do this multiplication, I want to divide one of these numbers by 8 if I can. Question 4. Black and white image takes 100 bytes to store. How many pixels are there? Black and white. 2 colours. How many bits does that need then? 1. Just 1 bit. So you know the colour depth is 1. So the answer is going to be 100. How many pixels are there? Okay, but it's bytes. The answer is 100 bytes to store. But remember, when we do that calculation, the answer is in bits. So 100 bytes is, when we go to bytes to bits, remember we multiply by 8. So 100 bytes is 800 bits. So 100 times 8 gets you 800 bits. If you had colour depth of 2 bits, then you'd have to divide that by 2. But because it's only 1, it's just 800. So, quick summary of that then. 100 bytes, turn it into bits, work out how many bits you need to store those colours, and then divide that. Right, question 5. An image has its pixels halved. What happens to the image size and quality? Try and be specific if you can. If you know the pixel size is halved, then you know the image size is halved. And the quality, we don't know if quality is going to be halved, because we don't know what the actual image is. But generally speaking, the quality is going to go down, but the image size will definitely be halved. And that would be the answer. Size is halved, but quality drops too. And this one, draw this. So if white is 0, so they told you what they are, so it's going to be 4 whites, followed by the next row is going to be 1 white, followed by the next row, which is 1 white, 2 blacks, 1 white, then 1 white, 2 blacks, 1 white, and then 4 blacks. So that's kind of what it'd be. That's what the pixels look like. 4 white pixels, 1 white pixel, 2 black pixels, 1 white pixel, like we just said. Yep, you know what's next. Edmodo, representing data, images, off you go. And a little recap for you. This episode was about images. What's a pixel? How are they used? How they're used in bitmaps? How does number of pixels and color depth affect file sizes? How does the number of pixels and color depth affect quality? And can you, using ones and zeros in binary, create simple images? Thanks. Next one will be sounds. Cheers.